Welcome to our discussion of Le Chatelier's principle. In this video, we will state Le Chatelier's principle, apply this principle to predict the shift in a reaction at equilibrium exposed to stress, and relate Le Chatelier's principle to KEQ. Le Chatelier's principle states that a system in equilibrium will oppose a change or a stress in a way that counteracts that change or stress. And there are three main types of stress that we're going to talk about that an equilibrium reaction will respond to. The first one is a change in concentration of either reactants or products once a reaction has reached equilibrium. The second is a change in temperature for exothermic and endothermic reactions. And the third is a change in pressure for gaseous systems only. In a chemical reaction, we can either add reactant or product to increase our concentration, or we can remove reactant or product to decrease our concentration. So in a system at equilibrium, adding reactant or product and therefore increasing our concentration of either will shift the reaction away from what is being added. If we take away or remove reactant or product, thereby decreasing our concentration of either, our reaction will shift towards what is being removed. For example, let's look at the reversible reaction of A to B, which is already at equilibrium. If we add A or increase the concentration of A, the reaction is going to shift to the right, away from what is being added, in order to use up that excess reactant and re-establish equilibrium. This means that our forward reaction rate is temporarily going to increase until we're able to re-establish that equilibrium. Conversely, if we were to remove A or decrease the concentration of A, our reaction would shift to the left, towards what is being removed, in order to replace and increase our concentration of A. So in this case, our reverse reaction rate is temporarily going to increase until equilibrium is reestablished. Another factor that a system in equilibrium will respond to is a change in temperature. For a change in temperature, we're actually going to just treat heat the same way we would treat any other product or reactant. So the shift due to a change in temperature is going to be very similar to what would happen to a reaction if we changed concentration of reactants or products, as we just saw in our last topic. So for an exothermic reaction, since heat is a product, adding heat or increasing the temperature is going to shift the reaction to the left, away from what is being added. Therefore, removing heat from an exothermic reaction is going to shift the reaction towards the right, or towards what is being removed. Conversely, for an endothermic reaction, since our heat is now a reactant, adding heat is going to shift the reaction to the right, where removing heat is going to shift the reaction to the left. The last factor we're going to talk about is pressure. And remember, a change in pressure is only going to affect gaseous systems. A change in pressure is most often due to a change in volume. And since a reaction has no control over the volume of the container that it's in, it needs to take a different approach when trying to counteract the change in pressure that it's been subjected to. Well, as we've learned in previous units, pressure is created by molecular collisions. And that is something a reaction can manipulate. It can manipulate the number of collisions occurring, thereby increasing or decreasing the pressure within that system. So if the pressure is increased, usually due to a decrease in volume, that's going to increase the number of molecular collisions. So our reaction is going to shift towards the side that makes fewer particles, or fewer moles. In the same way, if our pressure decreases due to an increase in volume, our number of collisions is going to decrease. So our reaction is going to counteract that stress by shifting to make more particles, or favor the side that makes more moles. So let's take a look at an example. In this reaction, A plus B gives us 3C. We have 2 moles of reactants and 3 moles of products. So if we increase our volume, we're going to decrease our pressure and decrease our number of collisions. So in response, the reaction is going to shift to the right because it wants to have more collisions, so it's going to shift towards the side with more moles. If we decrease our volume and increase our pressure, we're increasing our collisions, so the reaction is going to want to decrease the number of collisions by shifting towards the left, the side with fewer moles. It's important to remember that a decrease in pressure will not always shift a reaction to the right. It will always shift the reaction towards the side with more moles, which could be on the reactant side. That also applies to an increase in pressure. It won't always shift the reaction to the left, but it will always shift the reaction towards the side with fewer moles, which could be on the product side. So when you're trying to determine which way a reaction will shift in order to counteract a change in pressure, you need to think collisions. An increase in pressure means an increase in collisions, means the reaction is going to want to make fewer moles to decrease the number of collisions. A decrease in pressure is going to mean a decrease in collisions, so the reaction is going to want to shift towards the side that makes more moles in order to increase the number of collisions. So the forward and reverse reaction rates aren't the only things that are going to respond to stress to a system. The KEQ can also change due to stress, but the only factor that can change the KEQ is temperature. So remember, the KEQ is always the same for a particular reaction at a given temperature. So if we change the temperature, we're going to change the KEQ for that reaction. So remember, KEQ is a ratio of products to reactants. So if the change in temperature causes the reaction to shift to the right or favor the products, then our numerator increases, so our KEQ is going to increase. If our change in temperature shifts our reaction to the left and favors the reactants, then our denominator increases, so our KEQ value is going to decrease. So let's take a look at an example. For this reaction called the Haber process, how could we change the temperature, pressure, and concentration of our reactants and products to maximize the production of NH3? Pause the video, try to answer it, and then hit play again to check your answers. So here you go. In order to shift the reaction to the right, which would create more NH3, we could decrease the temperature. So removing heat, remember, is going to shift the reaction towards what is being removed. We could increase the concentration of our reactants, because if we increase or add reactants or products, it's going to shift the reaction away from what is being added. Or we could increase the pressure. If we increase the pressure, we increase the collisions. So the reaction is going to want to decrease the number of collisions by making fewer moles. And on our product side, we only have 2 moles, whereas on our reactant side, we have 4 moles. So to wrap this all up, let's watch 2 short videos as a review of Le Chatelier's principle.
In this lesson, you will learn about Le Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract the stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done. The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction. When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure. The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles, 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles. So in our example, equilibrium shifts to the left. So an increase in pressure favors the side with fewer moles, and a decrease in pressure favors the side with more moles. In our next lesson, you will learn about how a system works to restore equilibrium in response to changes in temperature. In summary, Le Chatelier's principle states that when a system at equilibrium is stressed, the system works to restore equilibrium. In this lesson, you will learn about how a system at equilibrium responds to changes in temperature. Le Chatelier's principle states that a chemical system at equilibrium always works to restore equilibrium when it is stressed. To consider what happens to a system at equilibrium when temperature is changed, you must first consider the energetics of the reaction in question. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Let's examine this hypothetical reaction where reactant A reacts with reactant B to produce product C and product D, with a change in heat of minus 75 kilojoules. This means that when the forward reaction occurs, 75 kilojoules of energy is released and 75 kilojoules is absorbed when the reverse reaction occurs. So an increase in temperature would mean that the endothermic reaction would be favored to remove the excess heat, therefore counteracting the imposed stress. Decreasing the temperature would cause the system to produce more energy, therefore the exothermic reaction would be favored. The dimerization of nitrogen dioxide to dinitrogen tetroxide is an exothermic reaction. Nitrogen dioxide is a brown gas, whereas dinitrogen tetroxide is colorless. What observations do you think can be made when the temperature is decreased? How about when the temperature is increased? Please pause the lesson to think about this and resume once you are done. A decrease in temperature favors the exothermic reaction, so more dinitrogen tetroxide is produced. Since it is a colorless gas, the mixture should appear paler. An increase in temperature favors the endothermic reaction, so more nitrogen dioxide is produced. The mixture should therefore appear darker brown. Addition of a catalyst does not affect the position of equilibrium as it increases the rate of both the forward and reverse reactions. It only quickens the attainment of equilibrium. Let's return to the example of you digging a hole and your friend refilling it while you dig. Imagine that you are both given much larger shovels. The size of the hole still remains constant, but with each dig or fill, more soil is removed or filled. In conclusion, when the temperature of a system at equilibrium is increased, the endothermic reaction is favored. When the temperature of a system at equilibrium is decreased, the exothermic reaction is favored. Adding a catalyst has no effect on the position of equilibrium.
So you don't need to know the information about catalysts. That's something that we won't cover for this particular section of this unit. But other than that, that concludes our discussion of Le Chatelier's principle. Bring any questions you have with you to class.